To understand the Boolean algebra, first we need to understand the logic functions or logical operations. Digital circuits perform the binary arithmetic operations with binary digits 1 and 0. These operations are called logic functions or logical operations. To describe the Boolean algebra, we used these logic functions. The algebra used to symbolically describe the logic functions is called Boolean algebra. There are four connecting symbols used in the Boolean algebra. First one is equal sign. So equal sign means whatever in right hand side which is equivalent to the left hand side. Second one is plus sign. The plus sign in Boolean algebra refers to the logical OR operation. Since it is plus, so you know it is OR operation. It means A plus B is equal to 1. So consequently, either A is equal to 1 or B is equal to 1 or both equal 1. Third symbol is multiply sign dot. The multiply sign in Boolean algebra refers to AND operation. The statement A dot B is equal to 1. It means A is equal to 1 and B is equal to 1. Dot means AND, plus means OR. Fourth sign is bar. The bar sign in Boolean algebra refers to NOT operation or the complementary operation. So if A is equal to 1, A bar means NOT operation, A bar is equal to 0. To describe the Boolean algebra, there are many theorems we need to learn. So few single valuable theorems are shown in the table. The single variable theorem means the theorem refers to the condition when only one input to the logic gate is variable. Only one input to the logic gate is variable. Like theorem 1, it is A plus 0 is equal to A. So here the A value is either 1 or 0 in plus sign. So we can use the OR gate. Later on we will prove this theorem, this old theorem. Here in this slide we just understand its forms. Theorem 2, A dot 1 is equal to A. Theorem 3, A plus A bar is equal to 1. Theorem 4, A dot A bar is equal to 0. Theorem 5, A plus A is equal to A. Theorem 6, A dot A is equal to A. Theorem 7, A plus 1 is equal to 1. Theorem 8, A dot 0 is equal to 0. Theorem 9, A double bar is equal to A. And here we can prove all these theorems. So like first theorem, A plus 0 is equal to A. So here A value is either 1 or 0. So a is equal to, in this input, a is equal to 1 0, and this is the OR gate. So 1 plus 0, output is 1. It means a plus 0 is equal to a. If you take 0, so 0 plus 0, output 0. Hence this theorem proved. Second theorem, a dot 1 is equal to a. Here also we can take a is equal to 0 and a is equal to 1 value. First we take a is equal to 0 and 1 input. So 0 into 1, output is 0. Because it's dot sign, so here is the AND gate. Right? And here 1 into 1, if a is equal to 1, 1 into 1, output is 1. Third theorem is a plus a bar is equal to 1. So if we take a is equal to 1 plus a bar, it means opposite of a, inverting of a. So 1 plus 0, this is OR gate, 1 plus 0, 1. Here also 0 plus 1, 1. Fourth theorem, a dot a bar is equal to 0. If we take a is equal to 1, a bar is equal to 0, a is equal to 0, a bar is equal to 1, and it is dot sign, so we can use AND. So 1 into 0, output is 0, 0 into 1, output is 0. Fifth theorem, a plus a is equal to a. So a is equal to 1. Here also again a is equal to 1. This is plus sign, so here it is OR gate, 1 plus 1, output is 1. 0 plus 0, output is 0. So a plus a is equal to a. Sixth theorem, a dot a is equal to a. So if we take a is equal to 1, here also 1, 1 dot 1, this is AND gate, so 1 dot 1, output is 1. 0, so 0, output is 0. And this is the seventh theorem, a plus 1 is equal to 1. So if you take a is equal to 1, here 1, so plus sign, so OR gate, 1 plus 1, output is 1. 0 plus 1, output is 1. 8th theorem, a dot 0 is equal to 0. If you take a is equal to 1, so 1 multiply 0, output is 0. 0 multiply 0, output is 0. This is I think ninth theorem. So a double bar is equal to a. And double bar means 2 times NOT gate. A is equal to 0. If you take a is equal to 0, a bar is equal to 1. Here is the NOT gate. Again bar, so another NOT gate. A double bar is equal to 0, because inverting of a bar, so a double bar is equal to 0. So a double bar is equal to a. Similarly, a is equal to 1, a bar is equal to 0, and again inverting a double bar is equal to 1. Now the next one is duality principle. The duality principle states that a Boolean expression remains valid if operator OR and AND are interchanged and ones and zeros in the expression are also interchanged. The Boolean expression remains valid if we interchange the OR and AND gate, and also we can interchange the ones and zeros. Let's understand that. In order to understand this principle, consider the Boolean theorem 1. So we know the Boolean theorem, a plus 0 is equal to a. Now we interchange this plus sign with AND gate. So the OR gate, we will put dot here, and instead of 0 we will put 1. So a dot 1 is equal to a. So note that this is the theorem number 2. What it means, what does it mean? The Boolean theorem 2 is dual of Boolean theorem 1. Boolean theorem 2 is dual of Boolean theorem 1, and vice versa. Similarly, the Boolean theorem 4 is dual of Boolean theorem 3. Boolean theorem 6 dual of Boolean theorem 5. Boolean theorem 8 is dual of Boolean theorem 7, like this, and vice versa. Okay, the next one is multivariable theorems. These theorems refers to the condition when more than one input to the logic gate are variable, like the commutative law, associative law, distributive law, and De Morgan's theorem. The commutative law is a plus b is equal to b plus a dot b is equal to b dot a. Associative law, a plus the bracket b plus c, so bracket will change, a bracket in the bracket a plus b plus c. Similarly, a dot b dot c in the bracket, a dot b in the bracket dot c, a dot b plus c is equal to a dot b plus a dot c. Distributive law, here a plus b dot c plus d, so a dot c, a dot c, b dot c plus a dot d plus b dot d. Theorem 16, a plus a dot b is equal to a. Theorem 17, a plus b whole bar is equal to a bar dot b bar. Theorem 18, a dot b bar is equal to a bar plus b bar. For solving the simplify the Boolean expression, we need to remember all these relations. So first one is commutative law. Commutative means theorem 10, 11. So commutative law. This law states that the order in which the variables are odd and end makes no difference. Whether it is a plus b or b plus a, no difference. So we can prove here plus sign means OR gate. So a plus b is equal to, in the input b a, so output b plus a. Similarly, here is the dot sign, so it's AND gate. AB output is AB. The input here BA, so output is BA. Another theorem is related to associative law. This law states that the ORing and the OR ending of several variables, the result is the same regardless of the grouping of the variables. Just here change the brackets, like a plus b plus c, here a plus b plus c. So similarly we can explain by this OR gate, here a, so a one input, and here b plus c, so bc. So this output is b plus c, and the final output is a plus b plus c. Similarly ab, so here a plus b, and here c input, so final output a plus b plus c. Similarly for the dot product, a, here we'll be using the AND gate, a and input, and here is the input bc, so output bc, the final output is abc. Here is the input ab and input c. Here is the output is the ab, and final output abc. Distributive law. This law states that a Boolean expression can be expanded by multiplying term by term, just the same as a ordinary algebra. You know the ordinary algebra. So a dot b plus c, so it means ab plus ac. So we can write this a dot. So here input a, bc. So input bc plus means OR gate, and here is dot means AND gate. So your output is a dot b plus c, which is equivalent to ab input AND gate because of dot, ac AND gate because of plus sign, it is OR gate. So ab, your final output is ab plus ac, and this is the theorem 16, I think. So a plus a dot b is equal to a. A plus a dot b, so we can write like by using the theorem 2, a dot 1 plus a dot b. If we taken out the common a, 1 plus b, theorem 14. We can also write a b plus 1 by theorem 10. Shows the two forms. First one is a plus b bar, a plus b whole bar is equal to a bar dot b bar, and second is a dot b whole bar is equal to a bar plus b bar. Here you can see you can convert the OR gate into AND gate, and also you can individually invert, and here OR gate to AND gate, inverted both individually a bar and b bar. So if we can say that when the OR sum of two variables is inverted, this is equal to the inverting each variable individually.